to welcome you to the 2013 Governor School of Engineering and Technology Final Symposium. I'm Eamon Collins, one of the RTAs that works with your students this week, these 4 weeks. We have some great presentations lined up for today, approximately 15-minute presentations with 5 minutes for questions. We ask that while presentations are being run, if you could please stay in the room. We can leave for the bathroom, try to organize it in 20-minute intervals if possible. For the mentors in the room, once your group presents, we would like to acknowledge your commitment to the program with a special gift. Just head out after they present, and then we'll give it to you in the auditorium. So we're going to get started with our first group, electric motor design.
All right, good afternoon, ladies and gentlemen. We are the Electric Motor Design Group. I'm Cole Harlan.
I'm Ellie Hollenborg.
I'm Zidia O'Hara.
I'm Austin Sherber.
And I'm Heather Torres. So today we're going to be talking about the physics behind electric motors, how electromechanical batteries work, how we design an electric motor that will also double as an electromechanical battery, the parts we selected for our motor, and the calculations we made with this design. So a typical electric motor consists of two parts, a rotor and a stator. A rotor is the rotating part that goes inside the motor, and typically the rotor has active wire coils wrapped around it. The stator is the stationary part that sits around the rotor and has permanent magnets inserted inside of it. So electric motors use the relationship between the permanent magnets and the active wire coils to exert torque on the rotor. So the active wire coils act as electromagnets, and the attraction and repulsion between these electromagnets and the permanent magnets is what causes the rotor to rotate.
The run force is the driving force behind electromagnetism, and it is caused by the interaction between the electric and magnetic field, and is defined as the cross product between the magnetic field, B, and the current, I. The run force is very important because it's used to exert torque, and torque is a moment of force. And many aspects affect torque, such as the length of the wire, the number of loops, the radius of the rotor, the magnetic field, and of course the current, which is all put together in the equation tau, which is torque, equals ln/RVI. Another equation for torque is tau equals Ki, where I is the current and K is the motor's constant, which is used to define the strength of the motor. A very important aspect of a motor is the angular velocity. Angular velocity is the rate of change of angular displacement, and for our motor we wanted to have a high angular steady state angular velocity, which means angular steady state is the highest velocity a motor can hit for a constant amount of time. It's defined as K over K squared plus beta, which is coefficient of friction times the resistance R, all multiplied by the voltage applied.
Our team didn't want to just make an electric motor that was spinning really quickly. We wanted to give our project a purpose. So the purpose we decided to give our project was that of an electromechanical battery. In order to take an electric motor and make an electromechanical battery, we added a flywheel, which is a circular object with a high moment of inertia. The momentum of the flywheel will keep the rotor spinning even after the power source has been removed. As the wires move through the magnetic field, current is generated and stored in the flywheel as kinetic energy. This energy can later be drawn on as a power source. So there are 4 main steps that we went through over the duration of our project. The first step was designing our rotor, stator, and circuit.
The image that you are seeing before you right now is a technical diagram of the assembly of our rotor and our magnet housing. Every one of the parts up there was designed by the team, was created in a 3D modeling program, and then prototyped on the 3D printer. So we're going to talk in particular about parts 4 and 5, which are the magnet housing and the coil housing. This is a technical diagram of the magnet housing. This was the part of the stator, so the part of the motor that stayed constant without moving. It was designed to hold 8 permanent magnets at even intervals, and the rotor would sit inside. We prototyped this part. This is a 3D printed prototype of the drawing you see up there, and it was made to fit the confinement limitations of the size of the magnets that were available to us and the size of the print bed of the 3D printer that it was designed on. This part is the coil housing. This is part of the rotor, so this part spins. It's designed to hold 8 coils. The coils would be powered and when wired. is powered in a coil, it creates an electromagnet, and the interaction between the permanent magnets and the magnet housing and the 8 electromagnetic coils on the coil housing would create the spinning of our motor. One thing we had to think about when designing our motor was the fact that the electromagnets and the permanent magnets would sync up as magnets do and opposites attract, and then it would be locked. So either the stator magnets or the rotor magnets had to constantly be switching polarities. And that way, when they began to attract each other, they would change polarities, begin repelling each other, and that's what would push them through. And that loop of attracting and repelling creates motion. We did this by creating coils that would be on opposite pieces of copper foil. So every piece of copper foil would have the negative or the positive end of a coil, but it would be the opposite end. So the coils were, the way the current was going was in opposite directions. This would make sure that every other coil had an opposite polarity. These would brush against carbon brush heads that were attached to the stator. The carbon brush heads wouldn't move. So the carbon brushes would stay steady and would either be supplying a positive or negative lead, but the coils would be moving. So they would constantly be changing. They would also always be opposite from the coil next to them. And that interaction is what creates a successful electro motor.
So the next step in our project was prototyping our system using three-dimensional modeling software.
We decided to use a program called Autodesk Inventor. Autodesk is a really easy user interface. It's very quick to pick up, and it's also free for students. It allows you to sketch parts and then extrude them into 3D and create them. You can then take these 3D parts and then assemble them together in an animated assembly, much like the one you saw a couple of slides ago. And that allows you to see exactly how your motor is going to be constructed when you put it together. Another cool thing it does is it lets you do 2 things from there. You can either make technical drawings, which are some of the drawings you've seen in the slideshow, that allow you to get your dimensions. It allows other people to take your part and then create it themselves. It provides a lot of information. It also lets you export them and 3D print them.
So the third step in our procedure was to select the motor parts that we couldn't use 3D modeling software for.
Alright, so beyond the design of our motor, the actual structure of the rotor and the outer casing, we needed to select parts that would not be 3D printed. The most important part was the different wire gauges that we could pick from. In this equation that was previously presented, torque equals various aspects that will change the torque of the motor. But 2 of them are affected directly by the wire. I, the current, and N, the number of loops. Regrettably, these are inversely related, so we have to be very careful to try and balance them out or pick the best one. There's one main difference between any kind of copper wire, the resistance, where larger gauge wires will have a very low resistance, and smaller gauge wire tend to have the higher one. It's kind of like a pipe. The larger the pipe, the more current can flow through in a smaller period of time. However, there's a trade-off. In the larger gauge wire, you get less loops per coil, which is the N value. So when we first went through, we actually thought that the larger gauge wire with the medium number of loops and the much lower resistance would be more beneficial for our motor. However, we were given a real-world limitation of 20 amperes, just to set a limit, and this would be divided among the 8 coils. So each wire is only actually experiencing 2.5 amperes of current at a time. And so we felt it would be more beneficial to use the high resistance wire because we would be utilizing the full potential of it, which it has a maximum holding capacity of 3.5 amperes, and we would reap the benefit of a much higher number of loops per coil.
So another part of our motor that we had to select was the magnets. The magnets were an extremely important part of our motor design because the strength of the magnet directly affects the strength of the motor as a whole. So the magnets that we chose were an alloy of neodymium, iron, and boron. They're 4 by 1 by 1/4 inches, and they generate a magnetic field of 1.38 Tesla. Another important part of our motor was the flywheel. So we selected a 27-inch diameter bicycle wheel that weighed 6.2 pounds to work as our flywheel. And the reason we chose a bicycle wheel for our flywheel is because bicycle wheels have most of their mass concentrated on the edge of their radius, and this gives bike wheels a very high moment of inertia, which means that the wheels get to keep spinning for a long amount of time, which would extend the battery life of our motor. The next thing that we chose was insulated copper wire. So as Austin just mentioned, we chose the 24 gauge wire, and we selected a total of 2,370 feet. Some other parts that we chose were carbon brushes, steel ball bearings, and copper foil. So the fourth step in our procedure was theoretically calculating values that would correspond to the strength and speed of our motor.
Yes, so as Divya just mentioned, we use many different equations to calculate many theoretical values. We are able to calculate the magnitude of our magnetic field, which we found to be 3.6 times 10 to the negative third Tesla. And then using tau equals ln RBI, we were able to calculate the torque per coil, which we found to be 44.3 newton meters. And finally, using tau equals Ki, we were able to calculate the motor strength, which we found to be 0.27 newton meters per ampere of current. Again, we were able to calculate even more results, theoretical results. We were able to find the friction to be around 1.1 times 10 to the negative 5 kilogram newton seconds per radian. Our loop length was 7.14 inches. Our final steady state velocity was around 44.4 radians per second. Our moment of inertia we found to be 0.31 kilograms per meter squared. And finally, our half-life of our flywheel was 5.42 hours.
Our group has worked very hard these past 4 weeks, and we are proud to be able to design a strong motor, which will also function as an electromechanical battery. We reused 3D modeling software in order to create our parts successfully, and we were able to do all this within our budget of $3 million.
And this is the completed rotor design that we have. This was all 3D printed in separate parts and then coiled. And this will, in our completed motor, be the center rotating piece. So this is the conclusion of our.
Along the way, we had several challenges. From the beginning, we did not have access to a machine shop, which meant that we had to find another way to create the custom pieces of our motor. We found that 3D printing would be a good option for us. Unfortunately, we had some technical difficulties with the 3D printer, and several of our first parts did not complete well, and so our motor was not built as we wanted it to be. By the time we had access to another 3D printer, which printed us these high quality parts, the program was at its end and we did not have time to complete the entire motor. Our group hopes to meet up again and finish building the motor at a later date.
For the future, we decided on many improvements that could be added to our design. The most influential improvement would be to reduce the friction. And we thought of two ways to do this: a vacuum chamber and magnetic bearings. The vacuum chamber would reduce any air drag that isn't reducing the speed of the flywheel. And if without that air drag, the flywheel would be allowed to spin for a much longer period of time. And magnetic bearings would remove any contact from the rotor to the outside casing, and so friction is obviously reduced. Another benefit of these magnetic bearings is that it minimizes mechanical wear, and that way our device could be used for a long period of time without suffering repairs. NASA actually uses very similar technology to this, and their flywheel has been proven to have a half-life of about 10 years. Another improvement that we thought of for our device would be to detach the flywheel after it has reached its steady state velocity. By detaching the flywheel, we remove any effect of the Lorentz force, which, as the rotor rotates within the magnet housing, a current is generated in the opposite direction of how it was previously induced. And so this effectively slows down our device. And we thought if we detach the flywheel, we completely remove the rotor from the equation, and the flywheel can spin without this reducing factor. While we see small-scale models not as a very effective thing for the future, it opened many ideas for large-scale energy alternative storage, especially renewable energies that does not have a consistent power supply. So solar power, which it only powers during the day, but people still need electricity at night, it could be recharged and discharged continually with minimal mechanical wear, and it would not lose its storage potential the way our chemical batteries would. So we found this to be a very beneficial technology for the future.
Before the conclusion of our presentation, we'd like to acknowledge a group of people. We'd like to thank Eileen Rosen, Director of GSET. We'd also like to recognize John Patrick Antoine, the Assistant Director of GSET, for helping us with our project. We'd also like to thank Brian Belvin, our mentor and RTA. We'd also like to recognize Professor John Pachowski for helping us with our 3D Jersey industries, New Jersey Resources, and the GSET alumni community, and as well as Rutgers University and the state of New Jersey for allowing us to have this unique experience. Thank you, and do you have any questions?
Yes.
It seems like it would be easier to put the magnets on the rotor rather than the coils on the rotor.
We did actually consider that idea for a long period of time, but we saw that the way to connect the current to the outer area of the motor would be carbon brushes. And that's very difficult to do with the oscillating magnetic fields if we put the magnets on the inside. So for our limited technology, it was much simpler to just put the wire on the internal rotor and go with that.
And an important aspect of electric motors is that these coils are electromagnets, which means you can change them. You can either turn them off and on or change their polarity. With putting magnets as the rotor and the part that's spinning and electromagnets in the outer rim, you'd have to do coils on the inside of a cylinder. And that's easy to do with today's technology in mass market, but we had to hand coil all of these. And it wasn't something that was feasible for us at the time.
Any other questions?
I'll ask them.
Without decoupling the magnet, so you keep the Lorentz effect going, do you find a way that you have an efficient flywheel that it could actually produce power back onto the grid or back onto the original place of energy generation?
Yes, we actually found our power output after the energy was stored. Because we said as the rotor spins within the magnet housing, it generates a current. And so if the flywheel is reattached to the rotor, which we would have to spin the rotor up to speed first, but once it's reattached, we would be able to draw from this power source and generate electricity in kind of in the same way that we input electricity. It just outputs in the same manner with the development of current. And we actually found our power output. Did we put it on this slideshow?
No, but it is in our research paper. You can find outside.
And our batteries technology is really similar to the way generators work, but instead of a crank, we have a flywheel. So you'd be able to pull the current back and use it for whatever you need.
So when it's built, how do you measure the torque?
Calculations.
You can use a difference between the values that we got that are actually physically measured, like length and number of coils and that, and then you can take the half-life, you can take moment of inertia, which are things that again can be physically calculated, and with enough things that are observable and actually you can gather data from, you can use those and use a little bit of algebra, and you can get the torque from there. I thank you guys very much.